So at this point, we finish our discussion on the effect of spin-orbit interaction on the hydrogen energy states, energies. So this is the first order shift. We see that really depends on the J, because different J will give you different values. Okay. And now, in a sample question last week, the TA worked out another effect for you, which is the relativistic correction. Later on, we need to also consider this effect, because if you have attended the exercise class last week, you should have seen it is of the same order, which is alpha square times some order one number as well. So if we take into account of this particular effect in hydrogen, we should be fair. And we should also take into account of the relativistic correction. I'm not going to work out that again for you here. You can refer to the relativistic correction sample question. But we should include that term into our consideration because the shift is just roughly of the same magnitude. That is a special effect for hydrogen. For bigger atom, the spin-orbit interaction term will be more important than the relativistic correction effect. And in those cases, we can focus only on the spin-orbit interaction shift. So we have done that. You have done that in earlier. There's a sample question working out this particular perturbation term. And then in sample question number 6, the first order perturbation was applied to this term. The calculation is not easy to do, actually. You have a momentum to the 4th power, okay? And then you have a hydrogen atom state on both sides. That can be skillfully turned into the potential energy V square expectation value, some combination of that. And at the end, this is the result. I quote the result and just would like to point out that it is the same order, alpha square divided by n square shift, and then again with an order 1 thing that has to do with n and l as expected. So this is of the same order of magnitude, and therefore we should put the two things together to be fair. Okay, we should not just a hydrogen stop here and done. Okay, because there is a similar order of magnitude effect. If we do that, then we get this final expression. I leave it as an exercise for you to combine these two expressions and then get into this one, okay? But this is interesting. Just to point out that Dirac obtained this particular form using his Dirac equation for an electron moving in a Coulombic potential. So this is the full result from one single particle relativistic quantum mechanical calculation. Let's observe the key feature. You see the prefactor is just the unperturbed energy. That's fine. So the 1 will represent, if you ignore everything, no spin orbit, no relativistic. Actually, there is another relativistic term that I don't want to mention here. Nonetheless, the 1 means forget everything, except the bare Coulomb potential. And therefore, the second term plus alpha square over n, this thing is all the perturbation term combined. We see it is of alpha square divided by, multiply into order 1 quantum number combinations. The most important point is the whole result at the end depends only on the principal quantum number n and j. Okay, not even on L. Well, that is a very interesting combination when you put this correction and this correction together, okay, and replace the quantum number by j. So what does it mean? Let's look at it in a graphical way. 1s, L is 0, j is half only, okay? So therefore, 1.5. So look at the ground state. If you don't have any correction, this is minus 13.6. But with all this correction come in place, this is lowered, but it is only one state because n is 1, j is half. Okay, so it shifts. But there's no degeneracy for it to removed. So there's one state, but shift. More interestingly is the 2s and 2p. Remember, when n is 2, 2s will only give you j equals half. But when L is 1, 2p, okay? 2p can give you j equals half as well. According to this expression, the origin from 2s here and from 2p, both of them corresponding to j equals half, should take on the same energy. Okay, that's why these two lines are drawn at the same energy, because they have the same n and same j. Only the other j value, j being 3/2, will give you a different higher energy here. Okay, now that is the prediction. When we include all the relativistic effect, recall, spin is also one of the relativistic effects, right? Because spin, if you want to get spin out naturally from an equation, that is the Dirac equation. Okay, we couldn't introduce you more to the Dirac equation because it's out of the scope of this course. Nonetheless, it is good to know that there is a relativistic consistent equation and give out this correction term. Okay, so now that is the prediction. Earlier on in this module, the first section, we look into data about this part of the hydrogen spectrum. Okay, at this point, we should be quite happy because at least we now understand why there is some splitting, and that splitting magnitude is correct. It's 10 to the minus 5. So we call it is one wave number out of 80,000. So it's about 10 to the minus 5, that kind of order. Okay, so we are there. Before we can compare with data, we need to learn how to communicate with experimentalists. So here comes a short section just to tell you how states are labeled, especially by those who do spectroscopy, 光谱学, okay? They have a convention, a set of symbols to label the states. So how to do it? The whole thing is called term symbol. And that is rather popular in chemistry book, but nonetheless, we need to at least know their labeling scheme. It's rather easy. We already discussed in hydrogen, our labeling uses L, S, and J for hydrogen. But you can imagine, for other atoms, you have 2 electrons, 3 electrons. We have to add up the spin angular momenta of the different electrons first, thereby getting a total spin that we use a capital quantum number to represent that it is a total. Similarly, you have many electrons, each has an L. You have to add the L of them and form a total orbital. So a capital L, and then you add this total L and total S together, you get really the grand total angular momentum with a capital J quantum number, okay? So usually you will see the capital thing rather than the lowercase thing. We use the lowercase things for hydrogen atom because we have been using the lowercase previously. And now, for hydrogen first, okay, so we first consider this. What is the term symbol? The term symbol is this thing. So just look at it. It's basically nothing, right? It just is a compact way to tell us the 3 numbers. L in the middle, the bigger one, okay? As a subscript, there's a J. As a superscript is 2s plus 1, not the s, but 2s plus 1. That it will be more convenient just to tell you the spin multiplet. 2s plus 1 is how many Z components hidden behind that s, okay? That is the term symbol. But there is one twist. Instead of giving you the number value of L, this L is represented in the traditional way. L is 0, is an S, so that will be confusion. This S is not the spin, this is the L equals 0, meaning 1 will be a P, 2 will be a D, 3 is a F, and so on, okay? So this is the term symbol, basically give us this information that we know already. That's how we label stuff, okay? So example, ground state, 1s, we know this, okay? L is 0 means it's an S, so we put an S in the middle. This is L equals 0. L is 0, S is half, J can only be half, and J goes subscript, okay? And S is half, 2s plus 1 is 2, so it's 2, okay? That represents spin up, down. That's it, if you know this scheme. So the term symbol for hydrogen ground state is this thing, okay? And very often, we supplement it by which configuration it comes from. So 1s, there could be a 1s in front, and then this term symbol. Okay, so this is a description of the term symbol of hydrogen ground state. If you go to excited state, there will be many other term symbols for the hydrogen excited state. For example, 2p. P is 1. P is L equals 1. And you represent it by a capital P. So this is here. Okay. But then you have 2 J's. Therefore, you will have this and that. 2 sets of excited states. Okay. And then you will have spin. But you will have only 1 electron. Spin is always half. Therefore, the spin multiplet is 2. 2s plus 1, okay? To make sure that you can trace where it comes from, this will be the label for the excited states, hydrogen. Okay, so complicated, but if you think about it, no more new information. And for general atoms, as I mentioned, you have many electrons. You could add up the L first to form a total L, a total S, then you add them up to form a total J using the rule, okay? And in that case, you follow the same scheme. In the middle is the L value. So this one, okay? And then after you use the rule to determine different values of J subscript, okay? And then depending on where you get here, okay, the S is 2S plus 1 up there. And that is the term symbol, all right? Now, why do we need that? For the reason that we will revisit this data. We have seen before this data, okay? In particular, now I would like you to look at this part, okay? The first 4 lines. Now you see the term symbols. Configuration 1s, it is a S, meaning L equals 0. You have a J here, half, okay? So actually it could appear here, subscript. And the 2 up there means S is half, 2S plus 1, okay? So this is the ground state, that's it. The ground state is defined it to be the 0 so that all the other thing looks like spectral lines, okay? The difference from the ground state. Now look at the 2S and the 2P. We saw that before, right? They are almost the same. But if you look into this 0.1 centimeter inverse digit, there is some fine separations. Okay? Now, in particular, look at this. J is half. That comes from 2S. The other J equals half. That comes from the 2P. According to Dirac's relativistic equation, it only depends on N, same 2, and J. Are they the same? Pretty good, right? The first 6 digits are the same. It is off by 0.04, maybe 0.03 something centimeter inverse out of 82,000 wave number. That is really good as a physical theory. Nonetheless, they are different. So there is still a small discrepancy between the relativistic quantum mechanics result and the actual experimental data. Okay, nonetheless, that difference should not be exaggerated too much. So let us look at that, okay? So you see, I focus on this thing, okay? Slightly different, but not much, okay? So I put this closer to each other so that you can compare, okay? But we do expect this to be different from that, from our fine structure calculation. This is spin orbit interaction we can already explain. J equals 3/2 should have a different shift from J equals half. So that is comfortable, no problem. The only thing that is slightly different is this the same J, and yet they are slightly different, okay? That is out of our expectation and out of Dirac's expectation. The same phenomena happens in the S3P 3D situation, okay? Again, you will have J equals half that could come from the S, L equals 0 plus half, that will give you half, and the P, L equals 1 minus half will give us a half. Okay, look at this. Again, it is even better than before. You see, it is 0.01 wave number out of 97,000 wave numbers. This is how accurate quantum mechanics already is. Okay, but yet some physicists were not happy about there is still a slight difference. Okay, and for n equals 3, there's another situation. You can take a p state L equals 1 plus half. The J is 3 half. You can take a D state L equals 2 minus half, that give you a 3 half. Now let's look at this. Are they the same? You see? That's pretty good for physics calculation, you see. Okay, now it's 0.0001 wave number out of 97,000 wave number. But still, almost identical, but still slightly different, okay? Again, if you go to the n equals 4, you will have more cases with the same n and same j. You see the accuracy is higher and closer, but nonetheless, for this j equals half thing, there is still a slight difference, okay? So let me conclude. So far, up to here, we are able to use very simple technique to study spin-orbit interaction, and we realize that the j, different j, will correspond to different shift and therefore remove some partially the degenerate state. And then in comparing with, including all the other effects, we have an expression. The shift is tiny because it is alpha square order times a order 1 a factor. Comparing with data, the calculation performs extremely well, I would say. Nonetheless, we observe some discrepancy. Okay, that's the conclusion. So here, I exaggerated a little bit, okay? Last term, you do this, and then you get this thing. I would say it's already 99% or more than 99% correct. And now, we know how to do a spin-orbit interaction, even relativistic correction, and we know technically how to label the terms and so on, okay? We find that our results is already good to 10 to the minus 5 to 10 to the minus 6, okay? So we are off by 1 out of a million, something like that, 1 out of 100,000 to 1 out of a million, 1 part. In a pictorial way, it is this thing. I repeat the graph here for our expression that we can get at our level. So it says it only depends on n and j. So we expect these two to be the same. Again, we expect these two to be the same. Okay, and also this to be the same. Okay, and so on. All right. And now we data set, if we look close into here, they are off by this tiny bit, the 2 n equals to j equals half set of lines. Okay, so that is what we saw. How we can resolve it? It is possible to resolve it, and that is why hydrogen atom has been a guiding light of quantum physics. the whole quantum mechanics starts from this Balmer series, Lyman series of hydrogen atom. We want to explain it. We have Bohr model, okay, as an intermediate step. Then we have Schrödinger's first paper solved the hydrogen atom. We are not satisfied. Then we have Dirac equation solving it, and we get this result. But when experimentalists work harder, they have more accurate, high accuracy. There's still discrepancy. And then theorists work to explain it, okay? But the story is that it is out of our ability at this level. This tiny difference is called the Lamb shift. I mean, this tiny thing, okay? And in order to understand Lamb shift, we must quantize the EM field before we can understand this tiny shift. It has to do with quantum electrodynamics. We have to use quantum electrodynamics to treat hydrogen atom so that we can at last get this very tiny part of the thing that we missed, okay? And that has been done very successfully. You can think that it is again hydrogen's data that has driven physicists to further develop the quantum theory from single electron theory to many electron theory, which is a field theory. That is the quantum electrodynamics. So a good way to learn quantum physics, I would say, is not to learn that many systems. For example, if you just get everything done about hydrogen, from the simplest thing up to the very advanced thing, only hydrogen, and then you have already acquired a lot of quantum physics. A picture to summarize everything. That is what we did last term. What you did last term, I didn't do it, okay? And that is the standard minus 13.6 over n squared EV spectrum. In our course, we have treated spin orbit, okay? We have also shown you how to do this relativistic correction. And then this is our prediction, okay? This is the n equals 2, 2s, 2p states, okay? 8 states all together. This is our prediction. We predicted that there only be, although they come from S and P differently, because they have the same J, they should be the same here. Nonetheless, observation said no, there's a slight split, and that can be explained by QED. It's the effect of the vacuum. So you have the proton, you have the electron, you have space here, and that is what caused this Lamb shift. Okay, vacuum is a lot of things. It's the ground state of the photon field. So this is the big picture that we conveyed. We cannot describe this a little bit for you, okay? But at least that points you, for those who are very interested in the further development, this is the beginning of QED. Okay, so this is a one-page summary. We have some techniques, we have some concepts, we have some reason. I hope you see the reason why we prepared to learn how to sum angular momentum, how to label them by J, for the convenience that we gained when we handle the spin-orbit interaction. Okay, so what's next? For those, this is outside our course, but I just want to guide you, okay? For those of you who are motivated, I want to learn more now, very exciting, and Lamb shift, what it is, okay? So the path to move forward is, first, learn something about the Dirac equation, which is for one electron. So Dirac only wants to do something that the equation is consistent with special relativity. That is to say, he wants to start with this. Okay? So the idea is if you can do this, then I can multiply a phi here, I can multiply a phi here, that becomes a IH bar d dt phi. Then I will have an equation that is at least consistent with relativity. Right? That's true. But a problem arises. If you plug in the h bar over I d dx operator here, you have something rather funny. You have an operator taking a square root, okay? And that is not comfortable to do. So Dirac thought of a very clever way. He asked, could this be written into a factor? Product of two factors, okay? So the meaning is that can this be written with at the end without any square root sign? All right. It happens that he could do it, but the smallest mathematical thing that he required to do it are 4x4 matrices. That is to say, he can remove the square root sign, but this sign become replaced by 4x4 matrices. The equation becomes a 4x4 matrix equation. And the lovely thing is that the solution of his equation to free particle automatically give us spin of the electron. And that is why we always say spin is a relativistic effect due to the work of Dirac. And if you understand this, you are able to put in the Coulomb potential into Dirac equation and obtain this result directly from the Dirac equation. Another lovely product of the Dirac equation is that we don't need to learn separately the spin-orbit interaction. If you put in the Coulomb any field into the Dirac equation, manipulate it, you will see when you take the non-relativistic limit, you will see the spin-orbit interaction term come out from the Dirac equation, okay? So that is another nice byproduct. But even so, you obtain an equation that meets the Lamb shift. For those who want to move further forward, that has to do with quantizing the vacuum, the EM field, and realizing that vacuum is something. And that has to do with quantum electrodynamics, okay? And that is the path forward. For the Dirac equation, there is a very short chapter in this quantum mechanics book that provides a very readable introduction to the Dirac equation. I think only 10 pages or so. And for those who want to learn quantum field theory seriously, I think this thick book is rather written in a rather very plain language, meaning the author works out the details for you. But the result is that the book is rather thick. It's about 600 pages, okay? But the nice thing is that technically you see how things are worked out, okay? And this will take you directly to the research level, right? Even this book was written for those who will do particle physics, but this hydrogen atom stuff is included there, okay? So this is optional, right? Don't take this and then spend your time too much on that. But for those who want to know the path forward, this is my suggestion. Okay, so any question up to here? Hello? If not, then let me motivate the last, the next part, and you will see hydrogen atom, equation, let me see. This is this one, right? Okay. Work for L equals J. Oh, okay, okay. Oh, where is it? Wait, let me look it up. Right? Part 5. Is it here? Somewhere here? I know which one you mean. I don't want to get into the detail, I know. You mean this thing? Is that right? Okay. Now let me. Now, I have hidden something under the rug, okay? Because I don't want to go into too technical, but I encourage you to look up the detail. Now, the hint here is the following. Actually, after work out, let me see. How can I put it? Okay. Now, if you look at the result somewhere here, okay? Now, first of all, let me announce it, okay? For the audience here, don't grab what I just told you, okay? For in this hour, okay? Get it, and then don't worry about anything. Here, there is one little thing. It's about the L equals 0 state, okay? Howard, you follow me, okay? That really has to do with you have J equals S, okay? And therefore, at the end, you will get at a L over L kind of situation. But if you think about the L equals 0 state, you don't have orbital angular momentum, and you don't expect anything about from the spin orbit interaction, okay? So nonetheless, this expression seems to be giving you us something. Actually, for that S equals 0 S state, L equals 0 state, we have to be more careful about this result. Okay, so at least you get my point. It's not about L minus half. It is about the S particular L equals 0 situations. Hello? Howard? Okay, is that okay? At least you understand what I'm saying. Okay, then One thing I didn't want to go into is the following. There is a third effect, okay, called the Darwin term. It is also a relativistic effect. Okay, but I don't want to mention in my notes because my focus is on the spin-orbit interaction, because that is kind of universal for many atoms. But the other two things happens to be more important in hydrogen because it's very light. And then for other atoms, not important. Okay, so at least you understand what I'm saying up to now? Okay, now there's some lucky thing that happens. If we include the Darwin term into consideration and include that result, at the end, everything goes into equation 27. Okay, so that is the long version of the story. But for teaching purposes, that is too much technical detail. Okay, I just want to show there is the spin orbit effect, and our tools have already set up to handle this term, say perturbation theory, easily. That is the point I want to get across. Okay? And that also, again, shows how wonderful this hydrogen atom system is. If you dig into every detail of the hydrogen atom, you learn a lot of things. Okay, so I will stop here for that remark. Okay, all right. Yes, yes, you are right. Okay, Zhang Ling, you are again asking about what happened here. Okay, if you are careful enough, maybe we should single out the S state, and that should have no defect, I think, because L0 you really don't expect to generate any internal magnetic field. Okay, I think what we got here will be something so-called mathematically is indeterminate. It's something like 0/0, that kind of things. Okay, that's why when I wrote this page, I could have stopped here, but then I say that may be lying to some of you. So I add into this remark, and I hope that at least for the big population of the students here, don't worry. Okay, there are technical things still for you to explore more. Okay, but for a few students who really care about every technical detail, there are something that you could do further. Okay, good. I'm glad that you noticed this tiny humble remark. Okay, now where am I? Okay, so now I would like to motivate a little bit about this final problem of hydrogen, or actually any atoms. At the very beginning, we mentioned the Zeeman effect, pretending we don't know spin at that time, only orbital angular momentum. We discussed the normal Zeeman effect, where one line split into three. Okay, with a magnetic field that will split the ML degeneracy. So P states, put 3, S, not nothing, you get 3 lines. one spectral lines get into 3 lines, and that is the normal Zeeman effect. Okay, so we have done that. But at that time, we ignored spin. Even pretended they don't exist. But now we know it's the spin. But at the same time, once we have spin, we cannot avoid spin-orbit interaction. Right? So that is a byproduct. Once you include spin into consideration, automatically you gain an internal magnetic field. So we just discussed the effect of this. And now let's put everything together. We bring back our external applied field. And we don't ignore spin. So we have spin-orbit interaction effect and an external magnetic field. Everything is there, okay? Now, we want to handle it in a very systematic way, okay? Not cheating, but just do it. Think about the physics. You have external field. We want energy terms to put into the Hamiltonian. Hamiltonian is energy. B field will interact with magnetic dipole moments. All right? Then look for magnetic dipole moments. If we have orbital angular momentum, we will have that one associated with L. This is the orbital magnetic dipole moment. We studied it before, Zeeman effect. Therefore, we will expect this interaction energy to appear in the Hamiltonian. That is due to the orbital magnetic dipole moment. But now we include spin. There will be a spin magnetic dipole moment. Therefore, we will expect the external field will also interact with the spin magnetic dipole moment. Therefore, there will be these two additional terms included into the Hamiltonian, okay, as well as the spin-orbit interaction, okay? So the physics becomes very rich. The Hamiltonian becomes, in the presence of an external field, and internal field, you cannot avoid it, becomes the part that you solved last term, spin-orbit interaction, and a Zeeman term. And what is the Zeeman term? It consists of two interactions. Orbital dipole moment, spin magnetic dipole moment interacting with the external field. All right. We could factorize that B out and call that there exists a total magnetic dipole moment that can be written as the sum of the two magnetic dipole moments. Then we see one troubling scenario. There is a G factor difference. There is a 2 here, there is no 2 here, because we can regard this as a G factor of spin being 2. Therefore, we realize that this Zeeman term has to do with L plus 2s, there is extra 2, rather than L plus s, which is J. So this is not J. This is J plus S. If you think about it, it's L plus S. Okay? So this is one thing that you should take note of, because one would like, we want it to be, okay? There will be a magnetic dipole moment associated with J. And therefore, we expect to see some J here and dot into the external field. That will be wonderful. Everything in the same form, right? Nonetheless, the difference in the J factor gives us some trouble. There is some extra 2, okay? So that is the point. Nonetheless, we know how to write down the whole Hamiltonian. Spin orbit, Zeeman, and the Zeeman is given by that, okay? Spin orbit is given by that, okay? So the whole problem is this. We have a long part with 2 kind of perturbative terms. Then you think, well, how can we handle it? All right? Now, just think in the most natural way, right? Of course, when you have 2 things to do in your life, what will you do? You will do the more important thing first, right? And then leave the less important thing later. In doing physics, of course, we do the same thing, right? So it's very natural. That is to say, I can tell you in general statement, we do this spin orbit first or do the Zeeman first. It depends on the situation, and that is a physics point of view, right? What do I mean by that? If you have a strong external field, that is to say, when B external is 10 Tesla, we know the internal field is about 1 Tesla. In this case, obviously, the external field wins, right, over the internal field, which is hidden here. You will expect Zeeman term will be more important than the spin orbit term, right? So depending on the situation, that is the answer. 2 opposite situation, strong B field, strong external field, do the Zeeman part seriously, more accurately, and leave this spin orbit as perturbation. On the other hand, if you are poor, you don't have money to buy a good magnet, your field is about 0.1 Tesla, 0.5 Tesla. First, do the spin orbit part. We just did it, okay? We know how to do it. Do this part seriously, more accurately, that is to say, invoke the J label, and then do this part. Take first order perturbation, it will work, okay? So that is the strategy we will do next time, okay? So in summary, the moral of the story is work on the more important thing first, all right? So do your problem set 2 and hand it in by tomorrow, okay? That is maybe the first thing to do in these 2 days, okay? It's common sense, all right? So in our situation, when one term between spin orbit and Zeeman is more important, do that part seriously. Try to do it exactly first, and then take the remaining part as perturbation. When they are comparable, sorry, we have to take the 2 parts and think what to do. That is very difficult thing to do, okay? So we rather buy a bigger magnet to avoid the problem, okay? Or tune down the magnetic field and avoid the problem. Worst of first, you have the Hamiltonian, you can do numerical solutions, okay? So I will stop here. Today, we will discuss these 2 extreme, 2 opposite limits next time and see how we can handle both spin orbit and external field together. Okay, so I will stop here today.